The idea behind spectral density is that a signal can be analyzed into harmonic oscillations. Such analysis gives valuable insight into the nature of the signal. Consider the communication signals carrying essentially random content over limited bandwidth, allocated to each such communication service. A communication signal can be modeled as a random process, and we manage to confine this random process into a portion of the spectrum so that it does not interfere with other such random processes in the other portions of the spectrum. Power spectral density is an important tool for the analysis of these communication signals and the systems that modulate, transmit, receive, and demodulate these signals. Here we focus our attention to wide-sense stationary random processes and introduce the power spectral density. Much more detail will be given under the spectral estimation topic. The power spectral density of a random process is defined as the Fourier transform of its autocorrelation. Consider the random nature of the process. The Fourier transform of each realization will also be a random process. What we are interested in is the spectrum of the statistics. The Fourier transform and the inverse Fourier transform presented in this slide operate on the autocorrelation and the power spectral density respectively. There are some important properties for a real random process. The autocorrelation is real and even. Remember that for a stationary signal, the autocorrelation depends solely on the time difference parameter. A change of sign of the time difference is the same as changing the order of the random variables in the joint expected value expression, which does not change the result. So the autocorrelation is real and even. The power spectral density is also real and even. When calculating the output of a linear time invariant system, we use the convolution operation. The system impulse response, ht, is convolved by the input process, xt, to obtain the output process, yt. The first order statistics of the output is easy to calculate. But instead of calculating the second order statistics directly, we can use the power spectral density. The fundamental theorem given at the bottom of the slide provides the method to calculate the power spectral density of the output from the input. The derivation of the fundamental theorem and the autocorrelation of the output sequence involves calculating the cross-correlation between the input and the system function, which we will not investigate at the moment. We just note that the cross-power spectrum is also defined and stop our investigation of the power spectral density here. There are three random processes that are of particular importance for the topics covered under the statistical signal processing course: the Gaussian random process, the white noise, and auto-regressive moving average processes, abbreviated as ARMA. The importance of Gaussian processes comes from two reasons. First, it's practical. An important property of Gaussian random processes concerns linear operations. If a Gaussian process undergoes linear operations, the outcome is again a Gaussian random process. Consider the LTI system description we used earlier. The convolution operation for calculating the system output is a linear operation where the random process xt is convolved by the system impulse response ht. If the random process xt is Gaussian, we can readily tell that the random process yt at the output is also Gaussian. Besides the preservation of Gaussian property through linear operations, there are other properties of the Gaussian random processes that are of great practical value. As you may remember, for Gaussian random processes, the wide sense stationary property is equivalent to strict sense stationary property. Mean and autocorrelation uniquely determine the statistics of a Gaussian random process. And for a stationary Gaussian process, the power spectral density of the output can be obtained easily by the power spectral density of the input and the system function. Besides the practical value, the Gaussian random process is actually a realistic model for many processes. There are many random processes that are the result of multiple random processes being added up. The central limit theorem tells that as the number of independent random variables being added up increases, the density function for the new random variable tends to Gaussian. This result for the random variables is also applicable for random processes. Remember, if we fix the time and focus on the controlling parameters for a random process, we end up with a random variable, and we can use the definitions and theorems developed in the context of random variables. Central limit theorem tells us that if a non-Gaussian random process goes through a system HD with long enough filter length, the output can be approximated by a Gaussian process. To better understand what is going on, consider the delay tap implementation of a filter depicted in this slide. Multiple time instances of a random process are being multiplied by coefficients and then added up. If the coefficients are of comparable values and the number of delay taps is enough, the output can be approximated as a Gaussian process. Here, we should note that the meanings of long enough and comparable should be analyzed specifically for each problem. The second random process in our list is white noise. Let's start with a very specific but also very common case of the additive white Gaussian noise. The term additive refers to the system model, where the noise is assumed as adding up with the output of the system to give the final noisy output. What is more interesting here is the term white, which is a reference to white light, composed of all the visible light spectrum. White noise has constant power spectral density, while our specific case has Gaussian distribution. Actually, any distribution with finite variance is possible. The most common naturally occurring process is the thermal noise. When sampled, the white noise yields random variables for each sample which are independent and identically distributed. Auto-regressive moving average processes combine two different models for random processes, namely the auto-regressive model and the moving average model. On this slide, we see the formal description of both models. The autoregressive model tells us that the current sample of the random process can be modeled by the linear combination of p past samples plus a white noise term and a constant term. Assuming such a model for a random process and estimating the coefficients phi and c, we can predict the future samples with some error from the white noise process besides the estimation errors in the coefficients. Moving average model, on the other hand, tells us that the process is the linear combination of past q samples from a white noise time series. Combination of the two gives us the ARMA model. This model is useful when the random process we are interested in is generated by an unobservable white noise process as well as a system transfer function. A brief search in the literature reveals the use of this model: modeling of traffic flow and forecasting, economics, modeling of river flows, electric demand load models are just a few such examples. So we finish our investigation of random processes. Thank you for your attention.